Hello, my name's Dan Justice here at the SEI, and today I'm here with Jason Larkin and Matias Jonsson. We're here to discuss quantum computing and a couple updates on our project. A lot has happened since the last time we talked. Matias is halfway through his internship. He's learned at least one thing or two. And since then, we were supposed to go to a conference, APS March meeting, right? But Jason, tell us what happened there.
Yeah, so the APS, it was supposed to happen, I think it was last week. And then with the coronavirus outbreak, they were mulling over whether to have the conference. And then right at the last minute, like the weekend before the conference, they decided they're going to shut it down. It was in the best interest of everybody. So that actually happened last week. And now we're seeing other closures and so forth. So I think it was like within the U.S., it was one of the first major events to be affected by the outbreak.
Mm-hmm. Yeah, I think in the end it was probably a good choice. I think a week later they start to actually see a couple of cases in Denver, right?
Yeah, dude, I was definitely thinking, like, I don't want to go.
Right.
I was going to go, but I was like...
to sum up, what were some of the things that you were planning on talking about at the APS?
Oh, yeah. So I was supposed to give a talk. We can provide the link in the
we can put
video, actually. And so the talk was concerned with looking at whether quantum computers, the noisy ones we have in this NISQ era, combined with classical computers in a hybrid approach, can provide advantage for certain kinds of optimization problems. So it was actually going to be in a session with like a bunch of other talks talking about this same kind of problem, these kind of variational methods. And so, yeah, that was the overview of it.
Do we have any plans to continue this work now that the March meeting is over? Mm-hmm. Are we looking for another conference? What's the plans going forward?
Both looking for another conference to go to with that work, and also a venue to publish it. And I think we found both of those. So, with APS come and gone, we'll be focused on the next few months in targeting this next conference and getting the work published.
Okay. So everyone, look forward to that in the future.
So recently there have been some papers that we found that had some more promising ways to explore like improvements to our abilities to do optimization problems on quantum computers. It's still not clear in the very large size limit how much of an advantage they'll provide, but we're still exploring that. There were a couple of statistical methods that we found in a paper from computational finance that were being used to basically amplify the tail of a distribution and optimize for the tail instead of optimizing for a mean. And that just results in possibly in the next few days we're going to find out how much of a better result we're able to get on optimization problems with it for different graph types.
Okay, that's perfect. How did you find that paper, by the way? Like, what in this internship has kind of led you to find like this is like potentially the golden ticket?
Google Scholar searches usually for keywords that are related to the problems we've been searching. Mm-hmm. Basically, this sort of the icing optimization problem, max cut, right? And Google Scholar searches on that, you start to see similar words popping up in several papers, and then you search for that word, and you see similar words popping up in other papers, and eventually, sometimes you stumble on a really good paper that it's maybe only been cited 5 times, but it actually has something that appears to be pretty good quality.
Well, this was a pretty new paper, right?
Right.
So it hasn't had a lot of time to be cited.
Of course.
This came out, in January? Maybe?
Something like that.
Okay.
No, it was actually like November. Actually.
Oh, okay.
And actually, it's even... So this is the... how do you say? This is the behavior of the publishing process. So this paper he's talking about, and many other papers... Yeah, many other papers like it. It actually... it showed up... It may have even been earlier than November, and then final publication comes months later. Mm-hmm. So... One of the difficulties with keeping track of research is keeping track of this delayed process where you have lots of work and these preprints make their way onto the archive, and then there's a matter of time to determine whether or not that preprint is going to transition into a published work, further legitimizing the work. And so there's these delay process. But if you want to be really on the tip of the research, you've got to be monitoring all these preprints that are being dumped on the archive all the time. And then you have to go on to further monitor who is the preprint from. Is that preprint going to transition into an actual journal publication? So yeah, that whole process means that there's new work, like every week there's something new.
Right.
Right.
So,
and a lot of new stuff.
So you can basically it's hard to know the quality of something that's just a preprint, because something that's a preprint on archive, it has a little bit of like quality control, but not a whole lot. So you can basically like look at those researchers and see what sorts of papers they've had published before to have an idea of like their like historical quality of papers. But just because someone hasn't necessarily published a big hitter paper before doesn't mean that this one isn't actually good, right? So it maybe gives you an idea of like how seriously should I take the ideas in this paper, but it doesn't necessarily guarantee anything, right?
Yeah, that makes sense. Plus, just by what you had said about the paper, it's a cross-disciplinary paper, right? It's bringing in finance, quantum computing, optimization, all this. Like, what made you think that a quantum computing paper on finance might be what's going to lead you to something?
Well, it's not that it's about finance. It's that it uses a couple of statistical methods that come from finance. Mm-hmm. Basically, when we're doing these optimization problems, the normal way that they've been done in the past has been to try and optimize such that the distribution as a whole moves towards the optimal value, right? But it's very hard to get the whole distribution to move, even with a really good optimizer. Just trying to sum it up in very vague terms. To move a whole distribution with an optimizer is actually kind of challenging. But this method in finance is to take the tail of the distribution and optimize such that the tail is stretched towards the maximum. And because at the end of the day, we only really need a couple of the values in the distribution to be as good as possible, not the whole distribution, right? Mm-hmm. So it's maybe easier to optimize the tail of the distribution than it is to optimize the whole distribution.
Okay, and then you said, did this paper say there was a theoretical or an empirical speed up on this problem?
They didn't promise anything, but they had suggestive results.
Okay.
Right, yeah.
And so your goal is to empirically show whether or not they exist.
Right. And so that could possibly lead to some interesting results for the paper that Jason is working on.
Okay, so we're looking to push all of this together and try to get squeeze the most out of it that we can. Right.
Yeah, think about it like these variational methods, these optimization methods that I mentioned. They're still quite new, and there's still not a lot that's understood about them, about their performance, and so forth. And so, like overall, our whole project, this whole team, I would say, its job is to be doing benchmarks and evaluations of these methods, and to try and incorporate new ones from the research community as they come along, and then judge their efficacy empirically with performance results. So we sort of have built our system such that we're constantly scanning the research space, right, for new methods, improvements that should lead to improvements in performance, and then judging whether or not that actually happens.
To clarify and go back a little bit, it's unclear if QAOA actually shows an advantage over any Clackle algorithm. Right?
It's still unclear. The community is divided on whether it will or will not. Some people claim it already does, but it's kind of iffy at best if it does.
Okay.
But there's definitely reasons to believe it still has promise.
Okay.
So optimization is one of the many different areas that people think there might be promise for quantum computers to be better. There's they're significantly more promising in terms of like it's basically known for sure that they're going to be an advantage, but optimization is certainly one of the more generally useful places. Material science is a very promising field in which quantum computers will absolutely provide an advantage, but optimization problems are still, they're quite valuable if it's the case.
Jason, why do you think that, why is chemistry or material science the spot where we know that quantum computers are going to show an improvement?
So, the easy answer is, quantum computers use quantum physics to do computation, and quantum systems are dictated by quantum physics. So, and that's a little bit like glossing over technical details, right? But I think that's the entry point to the intuition. Then from there, I think that so I think you have the same long-term, I won't say guarantees on performance improvement, but like in cryptography, you have this idea of, you have Shor's algorithm, and you have even resource estimates for when it would provide its advantage, the one that we know theoretically it should have. For material science, that same advantage can be projected for, we've talked before about FOMOCO and the nitrogenase process. I think that the challenge is not about, in material science, it's more about can we find that advantage soon? Like, can we find any advantage soon? That's where the computational complexity theory is lacking, is in like between 100 qubits, 1,000 qubits, and for given fidelities, everything way less than a fully scaled fault-tolerant quantum computer. Like, we don't know nothing about it. We know very little about inside that space. Okay. And that's what's frustrating, because you want to build these quantum computers, you want them to start being useful right away. You don't want to wait this long time period. But the computational complexity guidance is very little, or it's
right.
It's not
the theoretical computer science for classical computing has had like well over a century to develop. I mean, people were working on computational complexity for somewhat rudimentary things like before the 1900s, if I'm not wrong, like some really good mathematicians, right?
Babbage.
Yeah, right.
Without really realizing.
And so, like, theoretical computer science for classical algorithms has had much longer and much more people working on it. And so, like, it's basically an unexplored territory in which, like, there just needs to be more talented computer scientists working on it to really figure out the nitty-gritty of the math.
Yeah, I mean, I think that there's only a couple of scientists out there that are really digging deep. I mean, Scott Aronson's obviously going to be the first name there. But,
right. Yeah. I mean, his name is all over.
Right.
Right.
Yeah. He's been in the game for a while.
Yeah. Why not name drop a few people? So in terms of this computational complexity stuff, this guidance that we're looking for, not just for long-term quantum computation, fully scaled, but also the short-term. So these are like people that are working on, Scott Aronson you mentioned, the guy who worked on the theoretical foundations for Google's supremacy demonstration, the random quantum circuits and sampling. There's a few more names, right? There's Bremner, and he's in Australia. We have here on campus Ryan O'Donnell.
Ryan O'Donnell's good.
Who else am I? I'm trying to round up a list of names.
Ryan O'Donnell, yeah, he's got a great classical complexity perspective, right? He applies that to quantum constantly.
Yeah. So these are the people that we need, I think, more help from in terms of computational complexity algorithms in understanding exactly what do you aim at for a short-term quantum advantage. Because there's a big question mark there.
Right, because if you have 2 million qubits, we know, like hands down, we're going to see 2 million really nice qubits, really good quality.
High fidelity.
Like, we're definitely going to see these problems that are they're not just like, we'll be doing them better on quantum computers. We're going to be doing them, and they're not doable on classical computers, right? But for 1,000, which is like, I don't know, 5 years out or less, right? Like, what can we do? What can we do, right?
Oh, and
talking about that, quantum volume just saw a big jump.
I was just about to say we should bring that number in.
Yeah.
Although there's some criticism about how useful it is. I think it's useful.
For people who don't know what quantum volume is, it's basically a measure of not just like how many qubits you have, but also how deep you can stretch them before the quality falls apart, right? Because right now the qubits are very noisy, and so if you take like a very simple way to think about it is the number of qubits and the depth of it. And what's the area of that? That's the quantum volume, right?
Yeah. So, the height is the number of qubits. Right. So, we know that our number of qubits we have on a quantum computer right now is extremely limited. Right. Upwards, maximum around 50-ish, 70-ish right now. Sometimes up towards 100 for some really experimental computers. And then the width is what you talk about is that
how long it lasts.
Yeah, because a qubit will decohere into randomness the longer and longer you attempt to use it.
And so like increases in quantum volume allow you, yes, you can increase quantum volume by making you have more qubits, but sometimes that brings in even more noise. So also usually, right? And so just making them decohere slower is more significant because you can do more complicated computations. You don't just have to like limit yourself to like a very short sequence of operations. You can actually do more operations, even if it's on slightly fewer qubits, right? And so recently, a couple of companies have made some significant improvements in quantum volume. Yeah.
Here's my critique on that, actually. Wouldn't that be quantum area, right? That's a 2D. Shouldn't it be?
I guess.
Oh, but it's more than the number of qubits in depth. There are other parameters, and so it ends up being a higher.
I was oversimplifying it.
Those two are probably top, two of the most important. But yeah, there's other factors.
Yeah, it's a more complex computation.
You actually have to execute a circuit on the device to measure the volume. It's not as simple as just.
Is it a standardized circuit or?
Yeah, it's a Rance-Around quantum circuit.
Okay.
The HAR measure.
Yeah.
Heavy output. It's actually pretty much the same thing Google did in their experiment. The same circuit or same type of circuits.
Right, that makes sense.
Not exactly the same circuit.
No, we said that there was an improvement in
right.
volume.
Oh, yeah. There's a well. So first with the quantum volume, it's like what are the numbers right now? So IBM's chips, at least the ones they have measurements for quantum volume for, their best chip has 32. Mm-hmm. And then Honeywell makes an announcement that their new device, based on it's not trapped ions, it's neutral.
I thought it was trapped ion. I'm not positive.
But they claim a quantum volume of 64. Mm-hmm. Okay. And then the question might be asked: so, what quantum volume do I need to do something useful? Right?
Not just
100,
not
200?
just how many qubits, but what quantum volume? Because there's both plane. Like you could build 1,000,000 qubits, but the quantum volume could be a millionth of a qubit, right?
It could be one gate depth,
right? Because you can't run anything deep, right? So you actually have to. The quantum volume is just as important, or maybe more important than the number of qubits.
Right. So
that's more important.
That's interesting, right? Because if you think about it, there's the paper out there. What's it? How to crack RSA 2048 in 8 hours 10 minutes using 20 million noisy qubits.
So that's error corrected. So what's its quantum volume?
What's its quality?
Infinite.
It has to be finite to some degree, right?
Well, no. If it's error corrected, if you have implemented error correction properly, it's supposed to suppress errors down to a tolerance level indefinitely. That's the point of it. Well, there's a break-even point, and then you get past that.
So it's infinite because you can go on
Your
forever.
depth is
So you have like a length of L, even if your width is. Okay.
Yeah, if you have 50 qubits, but you can compute on it in principle forever. It wouldn't be infinite, but it'd be a very large number.
Right.
Compared to what we have now, it should be practically infinite.
So do classical computers technically have a quantum volume of infinite?
Or
right?
They don't do coherent.
All right.
Yeah.
We error correct classical computers pretty easily.
The errors that really creep in on classical computers is when you make them the transistors too small. Then you start getting the quantum effects creeping in, like smaller than like 50 atoms, right? And so like research in the classical space is done on electrical engineering is done on how can you like avoid that and actually make it smaller and keep what's the law on doubling.
Moore's
law alive, yeah. But that's something else altogether.
So one thing that I think in this near term where these quantum volumes are like 32 or 64 or hundreds, they're not practically infinite. They're not error corrected. So it seems that the community and the Google experiment it highlighted how important focusing on sampling-based algorithms rather than algorithms which seek to find some definite answer. So the whole Google experiment is based on sampling. And Matias was mentioning before about these variational methods and trying to look at those methods in terms of sampling. I think in the short term, it has to be a strategy that's focused on or looked at very carefully, these sampling-based approaches, because I think they're the type of approaches which I think can tolerate these short depths and this high noise. So I think, even in the variational methods we're looking at, there's already a shift towards sampling, and then the question would be, what other types of problems could we look at in sampling?
Okay.
But that seems to be, from what I can tell, one of the major themes of, coming from algorithm design, people in algorithm design and complexity.
Yeah, quantum complexity seems to be very interested in, I think, what they call quantum querying complexity, where you have a black box quantum algorithm, and you're only curious about how many times you have to query that algorithm in order to characterize what's inside of it.
Yeah,
right.
Yeah.
And so that seems
sampling.
to be so that seems to be a very common.
Yeah, and in
idea.
your term with limited resources, sampling seems to be the way, or to us at least, appears to be the most promising way to go, because the more fancy. Like Shor's algorithm and stuff, they are completely unrelated to sampling, and it's because they're just so, I don't know, it's not because they're so large. They're also so large, but the sampling type algorithms, for the most part, the ones we've seen, seem to be much more feasible in the near term. Is that fair?
Yeah, it seems like they're more tolerant of short circuit depth and of noise presence, or they could be in principle. I mean, Google at least demonstrated that with the random quantum circuits. Now the question is, what are some circuits that actually produce sampling or distributions which we want to sample from, like that, in machine learning or optimization or whatever. But yeah, it's at least one approach. I'm not saying it's the only one, but it's for sure common amongst different researchers that they think this is an important approach.
Yeah,
And for good reason.
To bring it back around to slightly more recent events, we of course have a slight issue with the coronavirus on. It's not here in Pennsylvania yet, right? But
there are some cases, right?
None confirmed yet in Pittsburgh. But
none confirmed yet.
By the time this thing goes online, maybe that'll change.
Hopefully not. Hopefully not. But classes are starting to get disrupted, right? Tell us about how are you as a student handling this?
We're switching to online classes as of next week, so I don't know. We'll see how that happens. But you're teaching a class, so how's that going? Justice is teaching a quantum computing class in the computer science department.
Yeah, so that class has been going really well so far. However, it's a little bit. It will be a stressor to have to teach it remotely. We're starting to try and adjust for that. One of the ideas that I think we're going to do is the final project. I think the students will need to actually make a video recording and present that on probably Zoom. I'm not exactly sure.
I don't know.
I'm not sure what platform we're using in order to communicate anymore. So
very up in the air right now.
We're in uncharted territory.
Yeah, this is sudden, and we're scrambling to have it done and still get the same amount of material out so that the students feel happy. We still haven't gone over Grover's or Shor's algorithm in the class,
right? Well,
and those are the big ones.
They're actually big for a reason. They're actually kind of both Shor's and Grover's algorithm are interesting in that they are kind of unicorns in terms of quantum algorithms. There aren't really any quantum algorithms that are very similar to them. Most of the quantum algorithms that exist or at least the promising ones, are Grover's and Shor's. Correct me if I'm wrong, but they require basically noiseless or error corrected, right? And there are many other quantum algorithms that are very much okay with it being noisy, right? Is that fair? Or
yeah, so the estimates for what problem size, for Grover's, for example, what problem size would yield a speed up? You find problem sizes which indicate a number of gates and so forth, which you would need error correction for. Mm-hmm. So I think that's fair to say. It seems for both practical application of them. For most practical applications, it seems like they would need error correction. I wouldn't say Grover's is so much a unicorn. I would say more Shor's.
And it's really interesting. Shor's algorithm is basically the algorithm that started the ideas of quantum computing as being something viable for
definitely got everyone's attention.
Yeah, it got people's attention because it basically allows for factoring of large numbers, which means cryptography isn't secure. If it works, then you can build a big enough computer. But then as people started researching more quantum algorithms, no one really found any other algorithms that were of that same sort of form as Grover's, right? It's kind of Shor's. It's kind of a uniquely formed algorithm in that, it was maybe the first one that was found for a quantum computer that was really useful, but there have been none since that look like it.
Well, it's a much simpler problem, but perhaps you could state that Deutsch's algorithm shows just as much of a exponential speed up as Shor's, but it's for a problem that we aren't really sure how to leverage, right? It's a computation that we can do faster, but we don't really know what to do with it.
Right.
And then, of course, like you said, then after that you had Shor's, and then did Grover's come before or after Shor's?
A little bit after.
I should know that one. Yeah, a little bit after. And that one's an amazing algorithm, but it doesn't show an exponential speed up. It shows a quadratic speed up.
Right, and just about every other quantum computing algorithm is really interesting. It only shows some sort of polynomial speed up, which basically it's a smaller speed up than an exponential speed up for viewers who don't know. So there's two really major types of speed ups. There's polynomial speed ups, which are big but not that big, and there's exponential speed ups, which are huge.
Right.
And exponential speed ups there's no proof anywhere mathematically that shows that quantum computers are actually capable of providing exponential speedups. As a matter of fact, many believe that they can't, which would mean that, interestingly, that the fact that Shor's algorithm exists for factoring large numbers with an exponential speedup on our classical algorithms suggests that there's actually a classical algorithm out there that might be able to do it in polynomial time, that just no one bright enough has spend enough time on it.
True, but there's also the argument that trying to prove or disprove that without actually finding the classical algorithm might actually also collapse the NP versus P problem, right?
Right.
Because because in order to prove that algorithm doesn't exist,
that's actually not
collapse.
true. Factoring is not provably NP hard.
Yeah,
Factoring is actually
it hasn't
not
proven.
proof.
It's not.
There's no proof.
It's
right.
strongly thought to be. Let's
It's
say,
strongly
or
thought to be, but there's no
proof.
actual concrete evidence. So what I'm saying is that the fact that there is a quantum algorithm that can factor in polynomial time means that there is a really non-zero chance
But there's
that
also
factoring is
a
actually a
classical
polynomial
polynomial
time classical algorithm.
Okay, so we're in a very gray area, right?
Right.
It's
Yeah,
still to be
It's
determined.
really interesting that all of cryptography basically is made weak if, in fact, someone comes up with a classical algorithm for factoring in polynomial time. Like all of the standards of cryptography that are widely used. There are a few niche ones that
Right.
but all of the widely used ones are made quite unsafe by the ability to factor, like elliptic curve cryptography and all of these other ones. So, yeah, I mean, research is being done by other institutions to try and come up with algorithms that are not weakened by this. But encryption algorithms. But none of them are definitely like, it's all gray area. Which one's going to be better? Or it's kind of post quantum cryptography is an interesting research area.
Okay. All right, that's it. Thank you so much for joining us, and we'll see you next time.